Hi everyone, we're solving this physics paper today. This is 9702, May June 2023, paper 4.1, as you can see over here. 9702, paper 4.1, May June 2023, physics, paper 4, A-level structured questions. So I know you have your exam on the 9th of October for the ones who are appearing for the October-November 2023 session. So which is why I've tried to fit this in my busy schedule for you guys, so that you can take a look at this before you start. By the way, quick disclaimer that this paper is the same as paper 4.3. As you can see that they have the same questions. So this is paper 4.1 as well as paper 4.3 is the same one. Here you go. Paper 4.1 or paper 4.3. This is the same paper. Anyway, let's take a look at the threshold before we begin. So for paper 4.1, A was at 62, B was at 50, C was at 40, D was at 30, and E was at 19. More or less the same difficulty as the other paper. The threshold hasn't changed much. So let's write that down. Out of a total available raw mark of 100, A was at 62, B was at 50, C was at 40, E was at 30, and D was at 19. So where should A star be at? As you can see, there's a gap of about 10 to 11 marks, 10 to 12 marks for each of them. So this should be at around maybe 72 to 74. That is what you needed to get that A star. Okay, so if you do solve this paper, match with the mark scheme, if you do get this answer, you are get this mark, you are good to go. Also, before we start, quick shout out to my Patreon. It's patreon.com/CAI paper solved. Please do consider supporting me on Patreon to unlock bonus perks. The first tier is just for support regarding question papers and exams. The second tier is for ad-free videos, access to ad-free videos, as well as my notes for physics and chemistry, chapter-wise notes for all the chapters, as well as access to all of my OneNote files, solved question papers for physics, chemistry, bio, paper 1, 2, 4, and 5, as well as math P1, P3, M1, and S1. Okay, for the recent years 2016 to 2023, and I also have the older years done as well, which you get access to in this tier, the ultimate learning experience, where you also get access to one-on-one video chats with me once or twice a month, along with access to private videos on particular topics, and your name in the credits on screen on all of my YouTube videos. Also, we have 3 members right now, so it would be awesome if you choose to support me here as well. Anyway, without further ado, let's start the paper. Starting with question number 1. I actually have this paper, like part of it done, part 1 done. So let's just go through it. So what is gravitational field? Before 2022, the definition of gravitational field was a region of space where mass experiences force. But starting from 2022, they have changed the definition according to the syllabus. Now, gravitational field is defined as force per unit mass. Similarly, electric field is defined as force per unit positive charge. Beforehand, it was region of space where charge experiences force, but now electric field has this definition of force per unit positive charge. And uh, you know, electric field strength and gravitational field strength. You might be familiar with those answers. It's force per unit mass and force per unit positive charge in the previous question papers, but now those definitions have been removed. In the paper, they will never ask you what is gravitational field strength, what is electric field strength. Rather, they will ask what is gravitational field and what is electric field, and these are the updated answers, okay? So please keep that in mind. Anyway, state one similarity and one difference between the gravitational potential due to a point mass and electric potential due to a point charge. So you guys know that the formula for gravitational potential is minus gm by r, and the formula for electric potential is 1 by 4 pi epsilon naught into q by r. So as you can see, the similarity is that both of them are inversely proportional to r. So inversely proportional to distance from a point, or other similarities include both of them are 0 at infinity. So 0 at infinite, 0 at infinite, 0 at infinite distance. And there is another similarity. Points of equal potential lie on concentric spheres. So they're basically talking about equipotential surface. Like for a spherical structure like this, the potential at this point is equal to the potential at this point as well. Okay, so that's what they've stated. You can also write that. Another similarity. Wait, let me just move this over here. There you go. So another point includes points of equal potential lie on concentric spheres. Fine. What about the difference between them? We know that gravitational potential is always negative. However, electric potential can be positive or negative. You can just write any one point. Any point is fine, okay? I think I should color code them, right? I think that would make things better. There you go. Okay. I missed this dot. Moving on to the next one. An isolated uniform conducting sphere has mass m and charge q. The gravitational field strength at the surface of the sphere is g. The electric field strength at the surface of the sphere is E. Show that m by q is equal to alpha into g by E. So clearly, since they've talked about the gravitational field strength and electric field strength, we need to take those into account. So the formula for gravitational field strength is small g is equal to capital G m by r square, and electric field strength is 1 by 4 pi epsilon naught into q by r square. These are the formulas that you need to have memorized. So as you can see from this formula over here, they have solved this as a ratio of g by e. So can we just do that as well? I'm just copying them. I wrote g by e, which is gm by r square divided by 1 by 4 pi epsilon into q by r square. I can get rid of the r square on both sides, numerator and denominator. And after reciprocal, 4 by epsilon naught actually goes to the numerator along with gm, and the whole thing is divided by q. Now here's the thing. I want g by e on one side and m by q on the other side. Now, that is exactly what I'm going to do. I have g by e on one side, and I'm going to keep m by q on the other side and transfer everything else to the side with g by e. So what does that entail? Capital G and 4 pi epsilon naught, I'm going to transfer them to the left side. Capital G and 4 pi epsilon naught, these two will be transferred to the left. See if that makes sense. So we ultimately end up with g by e times 1 divided by g times 4 pi epsilon naught is equal to m by q, where 1 by g 4 pi epsilon naught is a constant, which is denoted as alpha. Okay. Show that the value of alpha is 1.35 into 10 power 20. Pretty straightforward. Alpha is equal to 1 by 4 pi epsilon naught into 1 by g. As you can see from the data booklet over here, g takes a value of 6.67 into 10 to the power minus 11, and epsilon naught is 8.85 into 10 to the power minus 12. So that is 8 point, or we could just use the value of 1 by 4 pi epsilon naught as 8.99 into 10 power 9 times 1 divided by 6.67 into 10 power minus 11, which is 1.35 into 10 to the power 20. Is that fine? Let's move on to the next part. Oh, I haven't done this part. Assume that the Earth is a uniform conducting sphere of mass this. The surface of the Earth carries a charge of minus 4.80 into 10 power 5 coulombs that is evenly distributed. Use the information in B to determine the electric field strength at the surface of the Earth. Give a unit with your answer. Information in B. Okay. Let's use this equation. M by Q is equal to alpha G by E. M by Q is equal to alpha into G by E. Okay, so if you make E the subject, we actually end up with E is equal to alpha times G divided by, it's alpha times G divided by M, and the whole thing will be times Q. So afterwards, E is actually equal to the value of alpha, which is 1.35 into 10 power 20. We use the value up top. times g, which is the value of g at the surface of the earth, right? So that is actually equal to 9.81 times q, which is minus 4.80 times 10 to the power 5, and the whole thing will be divided by the mass, which is 5.98 times 10 to the power 24. Okay, so 1.35 into 10 to the power 20 times 9.81 times minus 4.8 into 10 to the power 5 divided by 5.98 into 10 to the power 24. So that gives us an answer of E is equal to minus 106. Honestly, you can ignore the sign. The sign doesn't matter. It's 106. Now, electric field strength has a unit of Newton per coulomb, or it could be volts per meter. You remember that field strengths always have dual units, okay? So either one works, Newton per coulomb or volts per meter. Also, notice how all the data has been given to three significant figures, which is why we are opting for a three significant figure answer rather than a 2SF answer. State how the direction of the electric field and the surface of the earth compares with the direction of the gravitational field strength. So we know that this is the earth and it has mass. So for any mass out there, you guys know that the gravitational field lines point inwards, right? So it's inwards. Now it is a charge with charge of negative. So any negative charge has electric field lines pointing inwards. So since it has negative charge, the electric field lines are also pointing inwards. So what is the direction of the electric field line and gravitational field line? They're in the same direction, that is inwards. That's why you have to say they have the same direction. Okay. If it was a positive sign, positive charge, it would be opposite. Moving on to question number 2. Let's do this. I'm just going to erase this part. A steel sphere of mass 0.29 kg is suspended in equilibrium from a vertical spring. The center of the sphere is 8.5 centimeters from the top of the spring as shown. Interesting. It has a mass of 0.29, so it also has weight. The sphere is now set in motion so that it is moving in a horizontal circle at constant speed as shown in figure 2.2. Okay, it is performing circular motion. This angle over here, according to geometry, vertical opposite angles, is also 27 degrees. The distance from the center of the sphere to the top of the string is now 10.8 centimeters. Explain with reference to the forces acting on the sphere why the length of the string in figure 2.2 is greater than in 2.1. So beforehand it was 8.5 centimeter, as you can see. Now it is 10.8. What is the logic behind this? Initially there was a tension in the spring which was just balancing the weight. Tension was equal to 0.29 times 9.81, and we know that the tension in the spring is actually F is equal to kx. So it was kx equals to 0.29 times 9.81. However, now what has happened exactly? If you look at this tension over here, now it is divided into two components, right? The weight is acting like this downwards, which is still 0.29 times 9.81. Now the concept is basically how much is that angle? 90 minus 27, which is 63 degrees. So basically this component of tension, or you could honestly just take the alternate angle. Like, let me show you. You could also do it this way. According to geometry, alternate angles, this one is 27 degrees, right? So let's just use that. Let's just use the same angle. Okay. So we can actually say now that, there are two components of t. T cos 27 degrees is actually balancing the weight. At the same time, T sine 27 degree is actually providing the centripetal force. It is the force towards the center. Okay. So basically, since it was vertical before and T only provided enough force to balance the weight, it was smaller. The extension was smaller. X was smaller. But now Since T is providing two things, it is balancing the weight as well as providing centripetal force, the value of T must increase. And if T increases, you guys know that T is equal to Kx, F equals to Kx, T equals to Kx, X is equal to T by K. Spring constant remains constant. If you increase the numerator, then the value of X will also increase. That is the logic, okay? So let's write this down according to the mark scheme. Let's see how much my words were similar to the mark scheme. Honestly, sometimes these answers are so difficult to score marks in, right? It's so vague. So they said that the horizontal force on the sphere causes centripetal acceleration, fine, which is being provided by tension. Now you can say that weight of sphere is now equal to vertical component of tension, or there was an alternate answer to point to the one I said, horizontal and vertical components of force now combine to give greater tension in the spring. Fine, that is the point I was talking about, okay? So there is now a horizontal force on sphere which causes the centripetal acceleration, and the horizontal and vertical components of force actually combine to give a greater value of tension. So since there is a greater tension, there should be greater extension. Greater tension in spring so greater extension of spring. Pretty straightforward, yeah? Fine, let's move on to the next concept. The angle between the linear axis of the spring and the vertical is 27. Yeah, we already know that. Show that the radius r of the circle is 4.9. So this is just trigonometry, right? This length is 10.8, hypotenuse. It's like this. This is 27 degree. Hypotenuse is 10.8. So we can just use sine 27 equals to opposite by hypotenuse. So sine 27 degrees is equal to opposite, which is unknown, r by 10.8 hypotenuse. There you go. So it's sine 27 in degrees times 10.8. So r is equal to 10.8 into sine 27, which is to two significant figures since our data is given to 2SF. R is actually equal to 4.9 cm. Fine. Next, show that the tension in the spring is 3.2 Newton. We can do this by balancing weight. I wrote this here, T cos theta. T cos 27 is equal to the weight. Okay, so let's write that down. T cos theta is equal to mg, which is the weight. So T times cos 27 is equal to, what was the mass? 0.29, right? Times 9.81. Fine. 0.29 times 9.81. So after you solve that, what do you get? 0.29 times 9.81 divided by cos 27, which gives us a value of T is equal to 3.2 newtons. Fine, shown. The spring obeys Hooke's law. Calculate the spring constant in Newton per centimeter of the spring. So we know that F is equal to Kx. Okay, F is equal to Kx, or T is essentially equal to Kx. Now, if you remember the graph, this is essentially the graph for force against extension. But sadly, in this particular question, we don't have extension, but rather we have the length of the spring. Okay, so the length actually, how much was the length? Initially it was 8.5. So the length was initially 8.5 and later on it became 10.8. Later on it became 10.8. So It's basically like this. Honestly speaking, wait up. It should be like this. 8.5. It should start from here and it became 10.8. Okay, so maybe it started from here at a value of what was the initial tension? Do we know? Initially, the tension was equal to the weight, which is 0.29 times 9.81 initially. This is the value of tension initially, which is 2.8449. 2.8449. Okay, so initially it was 2.8449 and then later on it became 3.2. Later on it became 3.2. Fine. So mainly remember that spring constant is the gradient of the fx graph or the f against L graph. But you have to ensure that you take the extension. Okay, the value of extension. Make sure that you don't take the length or else you will get a wrong value. Okay. So what is the change in tension? I want to find out this change in tension, the change in the y-axis. So del T is equal to final tension 3.2 minus the initial tension 2.8449 or 0.29 into 9.81. That's what they wrote in the mark scheme. So how much is that? 0.3551. That's del T. Now we know that K is actually going to be equal to the del T by del X. So if you input that, del T is actually this value over here, 0.3551 divided by the change in extension, which is in centimeter, right? So 10.8 minus 8.5. So answer divided by 10.8 minus 8.5, which gives us a value of 0.15 Newton per centimeter to two significant figures. Okay, that's 0.15 Newton per centimeter. Hopefully that's fine with you guys. Tricky question though. Not everyone's cup of tea. This whole paper is very tough. This whole question number 2. Use the information in B to determine the centripetal acceleration. So guys, we know that the formula of centripetal acceleration is basically the formula is A is equal to V square by R. That is one formula. We also know that it's F is equal to ma, so A is equal to F by m. So depends on what we have. Since we don't have the velocity but we have the force, which is T sine theta, and we also have the m, which is 0.29. So what do we get? A is equal to T sine theta divided by 0.29. So A is finally equal to 3.2 sine 27 divided by the mass 0.29. Let's do that. 3.2 sine 27 by 0.29, which is 5.0 to be exact, to 2SF. 5.00, 5.01 or 5.0 meter per second square. Since the data is given to 2SF, just go for 2SF answer. Calculate the period of the circular motion of the sphere. Interesting. Let's find out the time period. Using the formula, you can go for omega equals to 2 pi by t. But we need omega first. How do you find that out? We know that centripetal acceleration. There are multiple ways you could do this, honestly. We know centripetal acceleration is either v square by r or omega square r. Let's just go for omega square r. It's going to be faster. Omega square r. So omega square is actually equal to a by r, right? A by r. A by r. How much was r? 4.9 centimeters. Okay, but since this is in seconds, we need to convert this to meters. 0.049 meter. 0.049. So omega is equal to root over 5.0 divided by 0.049. Fine. Now, if you input this here, t is actually equal to 2 pi by omega. So t is equal to 2 pi divided by root over 5 by 0.049, or after reciprocal. Sorry, it's a bit. Wait. T is equal to 2 pi divided by root over 5.0 divided by 0.049. So let's solve that. 5 divided by 0.049 root over answer, then 2 pi by answer, which gives you an answer of 0.62 seconds. 0.62 seconds. Okay, moving on to question number 3. State the reason why two objects that are at the same temperature are described as being in thermal equilibrium. Okay, this is really important. To be in thermal equilibrium, there must be no net thermal energy transferred between two objects. Okay, so there is to be no net thermal energy. No net thermal energy is transferred between them. This is extremely important. Okay, now figure 3.1 shows the variations with temperature of the densities of mercury and of water between 0 and 100 degrees Celsius. Fine. Temperature may be measured using the variation with temperature of the density of a liquid. We know that all thermometers have a thermometric property and substance. What is the thermometric substance? It is a physical property which varies with temperature. It might be the density of a liquid. So that is why for measuring temperature over this temperature range, why is mercury suitable? Basically, a physical property is better if it varies linearly. Okay, so we know that the density of mercury varies linearly with temperature, which is why it is used in mercury thermometers, the clinical ones, right? On the other hand, water actually varies non-linearly. Okay, and look at the mercury. Mercury has unique values. This value never repeats. This value never repeats. But look at water. This same value repeats twice. It's not a one-to-one function basically, right? Like P1. It does not have unique values. Okay, so why is water suitable? So why is mercury suitable? Sorry. Firstly, the variation of density with temperature is linear. Fine. Or you could state that each temperature has a unique value of density. That's an important point that you can highlight. On the other hand, why is water not suitable? That is also important, mainly due to the fact that it is not linear. So that's our first point, that the variation of density with temperature is not linear. Okay, that's our marking point number 1. Also, they are not unique, or there are different values of temperature where the density is the same, right? So that is an alternate point, that different temperatures have the same density. Fine. Or, oh, you had to write any two from these. Okay, so these were not optional, you had to write any two. Or you could say that there's a turning point, right? Like in this turning point, you know that in turning points dy by dx is 0. So there is a point, or there are regions where the temperature, the density does not vary with temperature. Okay, that is a red flag. You can't have that. Different temperatures have the same density. That is the point we talked about. And region, there is a region where the density does not vary with temperature. There is a region where the density does not vary with temperature. Okay, now a beaker contains a liquid of mass 120 grams. The liquid is supplied with thermal energy at a rate of 810 watts. The beaker has a mass of 42 grams and a specific heat capacity of 0.84 joules per gram per Kelvin. The beaker and the liquid are in thermal equilibrium with each other at all times and are insulated from the surroundings. Figure 3.2 shows the variation with time of the temperature of the liquid. State the boiling point of the liquid. So what is the boiling point of the liquid? The point where temperature, even if heat is applied, temperature does not change because it is used up as latent heat. So how much is it actually? Uh, 10, 20, 30. Oh, it's not like that. So maybe 4 boxes are 10. 1, 2, 3, 4, 10. 1, 2, 3, 4, 20. Okay. So 1, 2, 3, 4. This is 90. 1, 2, 3, 4. This is 80 actually. So 4 boxes comprise of 10. So each small box is 2.5. So the boiling point is actually 80 degrees Celsius. Determine the specific heat capacity of the liquid. So we can actually use this information that for the first 21 seconds, the temperature increased from 25 to 80 for the first 21 seconds. So we are going to use the formula H is equal to mc del theta, Q is equal to mc del theta. Okay, Q is equal to mc del theta. So we know that Q is equal to mc del theta. So C is equal to Q divided by m del theta. Now the thing is, um, basically, sadly we do not have Q, but I think we can figure that out. How? The beaker has a specific heat capacity of this. The beaker has a mass of this. Now the beaker contains a mass of 120 grams. Okay, so this is the situation. The beaker contains a mass of 120 grams of water. The beaker itself has a mass of 42 grams and a heat capacity of 0.84. So when we heat it up, the beaker will gain heat as well as the liquid inside it. Now the beaker and liquid are always in thermal equilibrium, so they will have the same temp. And we are applying a wattage of 810. So using that, we know that power, where's the formula of power? Power equals to work done by time, or they used Q by time. So Q is equal to PT. We can find out the thermal energy supplied. It is 810 times 21 seconds. T is 21, I told you from the diagram. So we actually get Q is equal to, how much is it? 810 times 21, which is 17,010, or approximately 17,000 joules. Now, if you perform the working, basically this thermal energy is going to go to two places. Firstly, to the liquid as well as to the beaker. So it goes to two places, the liquid as well as the beaker. So let's try to figure that out, okay? So this is how I would do it, honestly. But I'll show you how they did it in the mark scheme. So this is how I do it. 17,010 is equal to mc del theta plus mc del theta. So 17,010 is equal to, the beaker has a mass of 45, was it? 42. 42 times 0.84, what is the del theta? It is 80 minus 25, which is 55, times 55 plus 120 grams times C, which is unknown, times 55. I just solve this and it would give me an answer of 2.3. Okay, C would be 2.3. But this is how they solved it. They wrote this equation over here, and then they found out thermal energy absorbed by the beaker separately. Okay, I'll show you what I mean, what they mean, sorry. So they found out the thermal energy absorbed by beaker. This is equal to mc del theta. The beaker had mass of 42 grams. It had a C of 0.84 and del theta of, I told you, 80 minus 25, which is 1940 actually. 42 times 0.84 times 55, 1940.4. Now finally, if you find out the specific heat capacity of the liquid, this C over here, basically this C, if you make it the subject, it is 17010 minus 1940.4 by the other stuff. Okay, so C is actually equal to Q, which is 17010 minus 1940.4 divided by the stuff for C, which is 120 grams of the liquid, times del theta, which is 5580 minus 25. Okay, so 17010 minus answer divided by 120 times 55, which gives me an answer of 2.28. C is equal to 2.28. However, since our data is given to a minimum of two significant figures, I'm going to opt for a 2SF answer, which is 2.3 joules per gram per Kelvin. Quite a complicated working, honestly, compared to other thermal thermal physics sums. Now, the experiment in C is repeated using water instead of the liquid in C. The mass of liquid used, the power supplied, the initial temperature are all unchanged. The specific heat capacity of water is approximately twice that of the liquid in C. The boiling temperature of water is 100 degrees Celsius. On figure 3.2, sketch the variation with time t of the temperature of the water between T0 and T60. Numerical calculations are not required. Okay, first things first, the horizontal section will not be at 80, rather it will be at 100. That is one marking point. It will be horizontal at 100. Also, it will be a straight line starting from, what was the initial temp? 25, and then it will go to 100 and become horizontal. Now it's all about the gradient. So what is the specific heat capacity? The thermal energy required to increase the temperature of unit mass by unit temperature, 1 Kelvin. Now it says that the specific heat capacity of water is approximately twice. So if you have more specific heat capacity, that means that you require more heat to raise the temperature by 1 Kelvin. Okay, so if you have a higher heat capacity, that means you require more heat. Higher heat capacity means more heat is required to increase the temp. So that actually leads to a flatter gradient. And flat by how much exactly? Since it's twice, that means the gradient will become half. Okay, so remember that greater heat capacity means more heat will be required, so more time will be required to produce that same thermal energy using the same power. And how much time? Approximately double. Okay, so beforehand, basically it reached 80 at 21. Now if I want half the gradient, it will reach 80 at 42. Over here it will reach 80 at 42, and so I just draw a straight line starting from 25, and it will pass through that point and reach 100 ultimately. Okay, so let's do this. Wait, I'll just erase this over here. There you go. So approximately double the gradient, and then we just have a horizontal line over here. Okay, sorry, approximately half the gradient. How did I find half the gradient? Before, at 21 it was at 80. Now at 42 it should be 80. If it has half the gradient, at 42 it should be 80. And yeah, I just follow that point. I draw a straight line passing through 25 and that point 42 80, and I just extrapolate it till it reaches 100 degrees Celsius, and then I draw the horizontal line. Okay, so this should be your only possible answer. Hopefully I could clarify, guys. So if you have double the heat capacity, the gradient will become halved, and if you have half the heat capacity, the gradient will become double. It's inverse. Okay, inverse related. Fine. Moving on to question number 4. State two basic assumptions of the kinetic theory of gases. Fine. We can go for easy ones, like the particles have negligible volume compared to the volume of the container. Negligible volume compared with the gas. They said compared with the gas. What else? The particles are in continuous random motion. Another one. The particles are in continuous random motion. Fine. What else? There are no IMFs between the particles except during collisions. So there are negligible, right? Negligible forces between particles. Negligible forces between particles except during collisions. Fine. And of course, all collisions are elastic. All collisions are perfectly elastic. And another important point is the time of collision is negligible compared to the time between collisions. Time of collision negligible. Time of collision negligible. Sorry about the handwriting. Compared to the time between collisions. Okay. By the way, this might probably be my last paper in a while because I'm really busy in the next few days. I might be going abroad for a trip soon as well in November. So I'll still try to release the paper 5 physics chemistry, paper 4 chemistry, the variant that I still have to do before then, and paper 1 as well. So keep an eye on the channel and do consider dropping a like and hitting the subscribe button, and also supporting me on Patreon if you love the content. Uh, the support would highly be appreciated because I'm technically doing this for free for you guys. I do get ad revenue, so yeah, you can turn off your ad blocker. It would help me as well. Also, do consider supporting me. Anyway, an ideal gas has amount of substance N. The gas is initially in state X with pressure 2p and volume P. The gas is cooled at constant volume to state Y with pressure P. Okay, so let's try to form a diagram of sorts. Then I think it would be easier for us. So firstly, the ideal gas has amount N. It is initially in state X with pressure 2p and volume V. Next, it moves on to state Y, where it has pressure P. It is cooled, by the way. This is a keyword. It is cooled. State X, 2pV, moles of N. At state Y, it has pressure P. And then it is then heated. So in this state, since it was cooled, it was minus Q. And by the way, it is an ideal gas, so it has no potential energy. Internal energy totally depends on, you know, internal energy totally depends on the heat, the temperature. Okay, so if temperature increases, internal energy will increase. If temperature decreases, internal energy will decrease, because it only has kinetic energy, right? Nothing else, no PE. So now the gas is then heated at constant pressure. Okay, so at constant pressure now what happens? The gas is heated, so it's plus Q now. We have constant pressure state Z with volume 2V. Fine. So the volume is 2V now. Finally, the gas returns at constant temperature to state X. Okay, so it goes to Z. Fine, it goes to Z and has a volume of 2V, but then returns back to X again. So this is the overall state. This is the overall state. Also, this does remind me of the question in variant 4.2. I do have a better explanation for that. I'll add this in the at the end of the video, where I do talk about it for variant 4.2. Determine an expression for the temperature T of the gas in state X in terms of Np and V. So we know that the general formula for an ideal gas is PV equals to nRT. Now we need to find out an expression for the temperature of the gas. So T is going to be equal to, what is the pressure? It is initially 2P times the volume V divided by nR. So this is the expression, 2PV by nR. So T is equal to 2PV by nR. This is our answer. And identify any other symbols identify any other symbols that you use. So we want to say that R is our molar gas constant. Okay, R is the molar gas constant at 8.31. On figure 4.1, sketch the variation with volume of pressure for the gas as the gas undergoes the three changes. The state X is labeled. Label states Y and Z. So X is labeled here, as you can see. So what does what does Z have? Z has a volume of 2V. So Z should lie somewhere over here. And for Y, we know that the gas is cooled at constant volume. So for Y, the volume will remain at V, but the pressure will drop to P. It is cooled at constant volume. I totally missed that. It is cooled at constant volume, where volume is constant but pressure drops to P. So this is state Y. And then what happens? We know that it is heated at constant pressure. So pressure will remain constant, but the volume increases to 2V now. So the pressure will remain constant at P, but the volume increases to 2V now. Okay, volume increases to 2V, and that is state Z. Now we are just asked to label states Y and Z. So we label them and sketch the variation with volume of pressure for the change for the gas as the gas undergoes the three changes. Okay, so we actually have to draw arrows as well for these changes. So let's go for it. So firstly, the change from X to Y will be like this. Okay, X goes to Y. And then the change from Y to Z should be like this. It changes at constant, basically at constant pressure. So, but the volume doubles. And at the end of the journey, what happens? It will come back to its original position, which is X, right? So at the end of the journey, you can just draw a line like this, an arrow. Actually, a line would be preferred. Here you go. There you go. Sometimes it's just so hard to draw. Yeah, okay. So we return from Z to Y ultimately. This is too long. I need to reduce the length. Oh god. There you go. Okay. So this is it. So yeah, according to the mark scheme, sketch straight vertical line XY from V to P to VP, fine. Then straight horizontal line YZ from VP to 2VP, and then curve with gradient increasing from Z to X from 2VP to V2P. Okay, so why is this important? Why is this always a curve? Mainly because why were the other ones straight lines? Mainly due to the fact that they said that the for X to Y the gas is cooled at constant volume, and in the next one the gas is then heated at constant pressure. So it meant that the volume never changes, so it remains vertical, and the pressure never changes, so it remains horizontal. But in this case, listen, whenever you move diagonally, okay, whenever you move diagonally, uh, there is no straight fact that you must be a line. There is no fact that you must be a straight line, okay? Because they just say that the gas returns to constant temperature. So always, if your movement is not, you know, at constant volume or at constant pressure, it will never be a straight line. It will always be curved. This is the main fact that you guys need to figure out. Okay, if your movement is not at constant pressure or at constant volume, otherwise it will always be a curve. Okay, you guys need to know. And it will be of increasing gradient. It won't be like this, okay? It won't be this shape, not with decreasing gradient. It will always be of increasing like this, okay? From z to x. This is the main fact that you need to know. So yeah, you could have lost 1 mark by drawing a straight line, so be wary. Now, during the change of state from y to z, the increasing internal energy of the gas is u. So you guys know that u is equal to del w plus del q. This is the general formula. During the change from z to x, the work done on the gas is w. Okay, fine. Complete table 4.1 to indicate for each of the 3 changes of state the increasing internal energy of the gas, the thermal energy transferred, and the work done on the gas in terms of P, V, U, and W. Fine. So let's go from x to y. So we know that from x to y, the gas is cooled. So since it is cooled, there will be a loss of thermal energy. However, the change occurred at constant volume. You guys know the formula of work done by a gas. It is P del V. If a change occurs at constant volume, del V is actually 0 at constant volume. Therefore, the work done will also be 0. So for change x to y, since it was done at constant volume, the work done on the gas is actually 0. This is your first step. Okay. Next, we'll come back here later. Now the gas is cooled at constant volume. Then the gas is then heated at constant pressure. So when you have constant pressure, you can use the formula P del V, and the volume increases from V to 2V. Okay. So from Y to Z, what is the work done? It is P del V, and it changes from like it is this is the change 2V minus V into P, which is VP. Now, whenever you have an increase in volume, it is actually work done by the gas, not on the gas. When volume increases, work is done by the gas, so work done is actually negative. So from Y to Z, since volume increases, work done is actually negative. And we will express that since we have P and V here, we will express them in terms of that. It is minus PV. Okay, since they told us to express it in PV, in terms of PV, U, and W. So for the first change x to y, since volume was constant, work done was 0. And for the next change y to z, since volume increased by v, and it's an increase in volume, so work is done by the gas, it is minus PV. So that is the next step. What else? During the change from y to z, the increase in internal energy is u. Okay, now we can actually use this box over here to figure something out. We know that the formula is u is equal to w plus q. So can we write this, that I'm doing it for this one currently. Wait up, let me just remove this over here. So yeah, for this one we know that plus u is equal to thermal energy, which is q plus w. We know the value of w, so plus u is equal to q minus pv. Therefore q is actually equal to plus u plus pv. So that is ultimately the working for the second one. So I've actually found out using u is equal to q plus w. I input the value of u and w. I got the value of thermal energy as plus u plus pv. That is my working. Okay, see the chronological order how I'm doing things. Fine. Next, let's go to the next one. Finally, the gas returns at constant temperature to state x. This is a very important finding. Okay, when you return at constant temperature, okay, I just told you that for an ideal gas, the internal energy, typically internal energy is sum of K plus P, but ideal gas has no IMF, so it has no P. It only has Ke, and the formula of K is 3 by 2 kT, where 3 by 2 K is a constant. So U is entirely dependent on temperature. So since for the change from Z to X, since for the change from Z to X, temperature remained constant, kinetic energy remained constant, and U also remained constant. So the change in U from Z to X was 0. This is a fact that you guys need to know. So any change that occurs at constant temperature, the net change in temperature will always be, sorry, if any change occurs at constant temperature, the net change in internal energy will always be 0. Now we can backtrack again, because we know that throughout the whole cycle, right? Throughout the whole cycle, I started from X and came back to X again, where my pressure is the same, volume is the same, N is the same, R is the same, and T is also the same. So what does that mean? Throughout my whole cycle, the net internal energy that I've gained is actually 0. So if you do the working, if you consider this as X, we can write X plus U is equal to 0. Therefore, X is actually equal to minus U. Okay, since the net internal energy change must be equal to 0. So minus U plus U is equal to 0. Now we can solve the others. Hear me out. We can go for minus U is equal to Q plus 0. So Q is equal to minus U. I'm simply using the formula del U is equal to Q plus W. Okay. So yeah, this is also equal to minus U over here. And for the last one, what can we write? 0 is equal to Q plus W. So Q is actually equal to minus W. Q is actually equal to minus W. So let's match. How did I do this? At first, I figured out a few things, that for x to y, since the change was at constant volume, this was 0. Next, for the change from y to z, since volume increased by v, and increase is associated with work done by the gas, so the value will be minus p v after working. P del v, so del v is v and p is p, constant. So increase, so the work done is negative. Okay, that's that. What next? Also, I know that the change z to x occurs at constant temp, so the change in internal energy is 0. Now, how did we solve this? I used this box using u plus q is equal to minus pv. So q is equal to u plus pv. And then I used these three boxes over here. How? I used the increase in internal energy unknown plus u is equal to 0. So the increase in internal energy must be 0 minus u, which is minus u. I found that out. And finally, I match these again using this triple box over here, and finally this triple box over here. How? For the one above, I used, what did I do? Minus u plus q is equal to 0. So minus u is equal to q plus 0. So q is equal to minus u. And for the one below, how did I find out the minus w over there? The 0 is equal to plus w plus q, plus w plus q. 0 is equal to plus w plus q. So q has to be equal to minus w. So that is how it was done. So hopefully you guys understood. Pretty complicated. These boxes have become quite difficult. Even I was struggling with the one in paper 4.2. These boxes are much harder than the ones back in the day, back when I gave A levels. So it's much harder now. Good luck with all of this. I will do a clarification on the one in paper 4.2 before ending the video. But before that, let's just move on to question 5. Okay, so how many questions do we have in total? Actually, I haven't checked. Oh, 10. So we will be done soon, hopefully. We don't have that much left, honestly. So starting with question 5. Part of an electric circuit is shown. The circuit is used to produce half wave rectification. Okay. So let's draw a diode. We need one diode for half wave rectification. So there you go. One diode. Next, A component is missing, complete the circuit by adding the circuit symbol. A capacitor C is shown. State the effect of V out. What is the role of V out? It is used for smoothing. So what happens to the output? It is used for smoothing, or we can just, its V out is smoothed. Okay, smoothed out. Okay, now figure 5.2 shows the variation with time of V in, the voltage that we are giving. Now I think we have to draw the variation. Oh, the variation of V out is also given. Determine the frequency of V in. Pretty straightforward. As you can see, the time period for every rotation is 0.04 seconds. So you guys already know the drill. Frequency is equal to 1 by time period. So frequency is equal to 1 divided by 0.04. 1 by 0.04, which is 25. That is equal to 25 hertz. Show that the time constant tau for the discharge of the capacitor through the resistor is 0.038 seconds. Okay, so this is the new addition to the syllabus starting from 2022. Tau is actually equal to, you know, RC. Tau, this symbol over here, is equal to RC. So basically, to find out tau, we need the value of R and C. But clearly, look at the next part. They've asked us to find out the value of C. So since we know that tau is equal to RC, and they've asked us to find out C in the next part, what does that mean? That means that we need to find out tau in another way in part 2 and then use that in part 3. So we don't use this equation now, but later. How else can we find out tau? Using the equation of discharging of a capacitor. Using the equation of discharging of a capacitor. So where is the capacitor being discharged in this V out circuit? So if we just performed half wave rectification, what would the circuit look like? It would look like this. Only this part followed by 0, then an increase. Only this part followed by 0 again. So how is this different over here? Match this graph. Match the one I drew. Okay, let me just copy paste it, right? It should be fine. So match the one I just drew with the one that is given. Wait, why is it much higher? What the hell? That's weird. It went above 0. I don't know if that's a printing mistake or something, but for some reason it has been amplified. Maybe for some reason it might be amplified, but basic thing is that it was supposed to be down here. If you follow this properly, it was supposed to be down here and then go up again. It was supposed to be down here and then go up again. However, due to the capacitor, rather than going down suddenly, it went down slowly. So this phenomenon of going down slowly, then going up again, then going down slowly, this overall process is called smoothing. Okay, so this section is unique, this section over here. And during this section, okay, this is the important part. During this section, the capacitor is actually discharging. During this section, the capacitor is discharging, and almost instantaneously the resistor is charged up again. So you guys need to appreciate the part where the capacitor is discharging. That's all you guys need to know. The capacitor isn't being used here. It is getting the supply from the current, but when current changes its direction, basically it's forward bias, right? So current can flow in this direction in the diode, but when the current changes direction, it can't flow through the diode anymore. But in that case, we don't take energy from the supply. The resistor does not take energy from the supply, rather it will take energy from the capacitor. So what is the initial EMF? It is, how much is it? This is how many boxes is this? Let's just check. Basically this is 2.5, this is 5, this is 7.5. So in total there are 10 boxes over here and 2.5. So 2.5 divided by 10 boxes, 2.5 by 10, that is actually 0.25 for each box. So 0.25 into 2 plus 5, that is actually 5.5. Okay, so the initial voltage is 5.5, and I'm going to use the formula V is equal to V naught e to the power minus T by RC, minus T by RC. Fine. And we know that tau is equal to RC. So let's just input the proper values. What is the final voltage though? I haven't found that out. So it is actually this 2.5 plus 0.25 into 3, 2.5 plus 0.75, which is 3.25. So our final answer over here is 3.25 after discharging. So damn, this was actually hard. 3.25 is equal to initial one, 5.5 times e to the power minus t by tau. So what can we write? 3.25 by 5.5 is equal to e to the power minus t by tau. And finally, after more working, ln 3.25 by 5.5 is equal to minus t divided by tau. And what is the time taken for discharging? It is from 0.02 to 0.04. So the time is actually 0.02 seconds. It is actually 0.020 seconds. So yeah, if I do the working properly, just one sec. Let me just bring it to the left hand side. Okay. So the final step is, after simplification, tau is equal to minus 0.020 divided by ln 3.25 by 5.5. Okay. So minus 0.020 divided by ln 3.25 by 5.5. So yeah, tau is actually equal to 0.038 seconds as shown over here. So since this was a hard one, that is why it was worth less marks, and it was a show question, so you could actually use it in the next part. Now find out the capacitance. So we actually know that tau is equal to product RC. So C is actually equal to tau by R. The R is the total resistance in the circuit, which is 14 kilo ohms, right? 14,000. So we use the given value of tau 0.038 divided by 14,000. 0.038 by 14,000, which gives us an answer of, one sec. Okay, so C is actually equal to, it's to two significant figures, 2.7 into 10 to the power minus 6. And since I use the SI units of seconds and ohms, it will be the SI unit of farads. Farads, 2.7 into 10 to the power minus 6 farads. Okay, that is the important part that you need to know of. Now the circuit in figure 5.1 is modified so that it produces full wave rectification. So we need 4 diodes in total. So just for the reason how V out now varies with time when V in is as shown in figure 5.2. Okay, so it will actually appear like uh, you know, direct current, because after full wave rectification it actually turns into a modulus. Okay, it will turn into a modulus. Basically this whole part will be reflected above. So this whole part will be reflected above. Oh, it was 5.5. It was 5.5. Check this. Sorry, I misunderstood. Here the scaling was different. 2.5, 5, 7.5. So here each box was worth 2.5 by 5 was worth 0.5. So it was 5.5 here, but since the scaling was different, it is zoomed in over here. That's why it did not overlap. Anyway, after complete you know, modulus, this part goes over here, and this part will also go over here, and yeah, it will be seen over here. So now what actually happened, it is appearing as if it's direct current, constant at a horizontal value. Okay, so it does not actually vary with time anymore after full wave rectification. Okay, so we have to say this, that V in has constant magnitude now in both directions, in both positive and negative directions. Fine. Also, so V out is now constant. Either you can say this, that it is now constant, or you could say that V out no longer does not no longer varies, does not vary with time. Fine, that is it. Okay, moving on to question number 6. So what is meant by magnetic field? So this is the definition which has not changed. This is the definition which hasn't changed. Electric field and gravitational field have changed, but magnetic field has remained the same. Okay, so what is it? It is a region where force X on, you have multiple options. You could either say, I prefer a moving charge, or you could go for a current carrying conductor, a current carrying conductor, or there was another alternate option, a magnetic material or a magnetic pole, a magnetic material or a magnetic pole. One second. Fine. Now, long straight wire P carries the current into the page. You know that cross refers to into the page. So we are using our right hand grip rule. I am putting my thumb into the screen and my other fingers are appearing as if they are clockwise. So draw 4 field lines to represent the magnetic field around wire P due to this current. Okay, fine. So we have to draw 4 concentric circles. The spacing will increase over time and the direction should be clockwise. Okay, so those are the facts that you need to keep in your mind when you do this. So that is one of them. Then let's go for the other one. Okay, now we go further and the distance will increase. Okay, it's a bit hard to draw honestly. So they've asked us to draw 4. Fine, so now this will have the greatest spacing. Here you go. I think we can just decrease it by a bit. Basically like this. Okay, I feel like it's okay. Look at this distance over here. Look at this distance, then this distance, and then this distance. It's increasing over time. Also, look at the direction. It has to be clockwise according to the right hand grip rule. If current is into the page, then the direction is clockwise. Okay, I feel like it could have been a bit better. Wait, let me just change it by a bit. Yeah, there you go. I think it's better now. Okay. Now, a second long straight wire Q carrying a current of 5 amperes out of the page is placed parallel to P. So one of the currents or one of the wires is carrying current into the page while the other is carrying current out of the page. As a result, they are carrying current in opposite directions. So this indicates that they will repel. Opposite direction means repel. The flux density of the magnetic field at wire Q due to the current in wire P is 2.6 millitesla. Calculate the magnetic force per unit length exerted on wire Q by wire P. So the thing that you need to understand here is that it's kind of interesting. I was just teaching this to my students the other day, the same topic. just the day before yesterday. So mainly wire Q will feel a force due to the field of wire P, and wire P will feel a force due to the field of wire Q. Okay, that's the main concept. Like one wire feels a force due to the other wire, like Newton's third law. They follow Newton's third law. Calculate the magnetic force per unit length exerted on wire Q by wire P. So we are trying to find out the force on wire Q, FQ. So we will be using the current in Q, but the field of P exerted on, this is the keyword, by wire P. Okay. So FQ is actually equal to, we know that F is in general. Let's write down the formula first in general. We know that F is equal to BIL. Now we want to find out FQ. FQ is equal to the B of P, but I of Q, and times length, but it's force per unit length, so I'm just moving L to the left side. Now what will the force per unit length actually be then? The flux density at wire Q, due to the current in wire P is 2.6 millitesla. They could have tricked you, honestly. They could give you both the field strengths. They do in some questions, so you need to choose one particularly. But it became too easy over here because they only gave you one magnetic field strength, right? So this is the magnetic field strength due to the current in wire P, which is being felt by wire Q. Okay, so I'm going to input this value over here. So let's do that. That is 2.6 millitesla into 10 to the power minus 3 times the current in wire Q itself, which is 5 amperes. Okay, so what do we get? 2.6 into 10 power minus 3 times 5, which is 0.013. Okay, so one more time, the force per unit length felt by wire Q is due to the magnetic field strength of P, but the current in Q itself, which is 5 amperes, and the magnetic field strength produced by wire P at Q is actually equal to 2.6 millitesla. Okay, so we end up with 0.013. That is our final answer. Newton per meter. Next one, state the direction of the force exerted on wire Q by P. Basically, opposite direction means that they're going to repel. So wire Q will feel a force towards the right due to wire P, and wire P will feel a force to the left due to wire Q, the field of wire Q. State the direction of the force exerted on Q by P. On Q. So Q will feel a force towards the right. So see, you don't even have to use the use Fleming's left-hand rule here. If you know that they're carrying current in opposite directions, they'll just repel. That's the trick, okay? And I could show you. That how left-hand rule is applied. Let me show you. So basically, wire P is carrying current into the page. So if you draw the diagram properly, it's basically clockwise current in clockwise direction. The magnetic field lines will be in a clockwise direction. Okay. So if you use your left hand rule over here, the current of 5 amperes is coming out of the page. So the middle finger will point out of the screen and the index finger will point downwards. So my hand is on top of the screen. My middle finger is coming out from wire Q and my index finger is pointing downwards. So my index finger is like this downwards and the middle finger is over here. It's coming out of the screen and the thumb is pointing in this direction. So that indicates the force, okay? And my index finger actually represents the direction of the magnetic field and the middle finger, which is coming out of the screen, is indicating direction of the current. Okay, so force is felt to the right, but this is totally irrelevant. You can directly find it out, right? Because they're carrying current in the opposite direction. So the force felt by both wires is actually the same because it depends on the product of the currents rather than the individual currents themselves. Okay, they follow Newton's third law. The flux density of the magnetic field at wire P due to the current in wire Q is 1.5 millitesla. Determine the magnitude of the current in wire P and explain your reasoning. So here we had to use that concept that I was telling you, that the force per unit length for both wires is the same because they follow Newton's third law. Force per unit length has the same magnitude has the same magnitude due to Newton's third law. Fine. Equal magnitude but opposite direction, okay? It's just that when we find out the force per unit length of P, we are going to use BQ, magnetic field strength of Q, but current of P, right? So we are going to use this value, where Fp by L is equal to BQ times IP. So we can write 0.013 is equal to, we know the magnetic field strength due to wire Q, that is 1.5 millitesla, 1.5 into 10 power minus 3 times IP. So let's do that. 0.013 divided by 1.5 into 10 to the power minus 3, which gives us a value of IP is equal to 8.67, or rounded off to 8.7 amperes, to two significant figures. Really good question, in my opinion, and good for practice. Everyone should look into this if they want to revise parallel wires carrying current. All right, let's move on to question number 7. Okay, so what is meant by the de Broglie wavelength? Basically, we know that the formula for the energy of a photon is E is equal to hf. And there's another relationship between wavelength and momentum. All moving particles have a wavelength. Okay, so that the wavelength associated with the moving particle is called the de Broglie wavelength. Now, so the relationship is lambda is equal to h by p. That means they are inversely related. So let's write down the answer. It is the wavelength associated with a moving particle. Very important. Okay, so this is it, where lambda is equal to h by p. Now, figure 7.1 shows a glass tube in which electrons are accelerated through a high potential difference to form a beam that is incident on thin graphite crystal. After passing through the graphite crystal, the electrons reach the fluorescent screen. The screen glows where the electron strikes it. So it forms a pattern like this. Now, this particle is reminiscent of, wave nature. Electrons are particles. So when this experiment was carried out, scientists were so confused because uh, the pattern that we expected were these specks of light, because electrons are particles. When they strike a fluorescent screen, they'll produce specks of light. But provided that we give it a proper diffraction rating that this graphite crystal is providing, it can be seen that the electrons actually diffract to form waves, and which gives us this pattern. After passing through the graphite crystals, the electrons reach the fluorescent screen. The screen glows where the electrons strike it. Figure 7.2 shows the fluorescent screen viewed end on from the right hand side of figure 7.1. So what is this phenomenon demonstrated by the pattern? This particular pattern is it's called electron diffraction. This phenomenon is called electron diffraction. Very, very important. We need this. And what can be concluded from the pattern in 7.2 about the nature of electrons? So it can be determined that electrons are actually behaving as waves rather than particles. So this is how we write it. So we have to say that the beam spreads out. The beam spreads out, indicating diffraction. Or an alternate marking point for this was, this is typically like an interference pattern. Remember in AS, back in AS, you guys did, the interference pattern, Young's double slit, where we got this regions of bright light and regions of dark light. That was an interference pattern. due to superposition. Or the alternate mark for this point is that light and dark regions indicate an interference pattern. Indicate an interference pattern. Fine. Now, what about the second point that we need to get? There is the one I was telling you, that the electrons are behaving as a wave, or according to the Marx scheme, the electron beam is behaving as a wave. This is the important point, okay? Because the beam spreads out rather than being specks of light. It spreads out, indicating that the electrons are behaving as waves rather than particles. Now the electrons in B are now accelerated through a greater potential difference between the cathode and the anode. On figure 7.3, sketch the pattern that is now seen on the fluorescent screen. So this is important because they are accelerated through a greater potential difference. So a higher PD indicates that the electrons will have more energy, and we know that E is equal to HF. So if energy increases, Planck constant being the same, the value of frequency will increase. Now you guys know that if frequency increases, then what will happen to wavelength? The wavelength will decrease. Now, what impact will this have on the diagram actually? Basically, as frequency increases, we know that the de Broglie wavelength is like this. De Broglie is equal to h by p. Or you could think of it this way. Since the particles or electrons are accelerated through a greater potential difference, they have higher velocity, they have higher momentum, and if momentum increases, since they're inversely proportional, lambda must decrease. So if we talk about concentric circles, beforehand, if the pattern was like this, now the rings must be closer together. That means that lambda has decreased. The gap between the rings actually refer to the wavelength of the particle, okay? That's what you need to know, that the gap between the concentric rings represent the wavelength of the particle. So according to the Marx scheme, it's stated that there should be a central blob and concentric rings, and the rings are closer together than previously. So this is the pattern. So we need a central blob at first. I can actually show you an example. Feb March 2022. Let's still check though. Yeah, this one over here. It's got this pattern. Beforehand, we had a pattern like this, but now the gap between the concentric rings is much smaller. Okay, so that's the general idea. So that's what we have to do over here. So we have to draw the central blob at first, but afterwards the rings will be closer together compared to the previous state. So we have to draw a central blob. My bad. Right, here you go. Afterwards, we are going to draw some circles over here. Okay, one more. But the problem is, in the previous figure, I don't see multiple rings over here. Probably they were talking about this. This is one of them. Well, this is the other one. So essentially this was the wavelength, but now it's going to be closer, right? Probably that's what they meant. So why don't I just show you here? Wait. So before it was like this, right? Now it just has to come closer. Maybe it's gonna be something like this. There you go. And let me copy the blob actually. Wait up. This should be the blob. So there should be this blob at the center. Let me just bring this over here. Followed by these lines like this. So just give multiple concentric circles, but they will have wavelength less than before. Sorry, I overcomplicated things. I did not get it at first. So how many rings were there initially? There was a central blob, one ring out over here. Yeah, you can just draw one more. That's also fine. There's no issue if you draw another one. It's totally fine. There you go. You can draw a diagram like this. Or I could make it better. Wait. Let me show you. This is kind of overkill, but yeah, this is what it should be like, honestly. Okay, the concentric rings are closer together compared to before. Basically you needed to show that this wavelength over here is decreased in length. Okay, that was done by showing this already, but it's fine. You could just show more. It's okay. Explain with reference to the de Broglie wavelength the change in pattern. I just told you that lambda is equal to h by p. So since it's accelerated through greater PD, the momentum is greater, so wavelength should be lower. Okay. So there is greater potential difference. So electrons have greater momentum. Next, since there is greater momentum, so there is a decrease in de Broglie wavelength. Sorry. So there is a decrease in the de Broglie wavelength. And finally, there will be a decrease in fringe spacing. Now you could word the last one in multiple ways. You could say that there is a lower de Broglie wavelength for same spacing in crystal. Like we have the same spacing in the crystal. You guys know this from AS, right? Like, check this. What causes good diffraction? The wavelength should be comparable with the slit width, right? If you decrease the slit width and, you know, or keep the width slit width the same, for this case it's graphite. If you keep the slit width the same and increase the wavelength, what actually happens? The angle of diffraction will actually increase. So what happens here? We actually lower the wavelength, right? If you lower the wavelength, that will actually lead to a smaller diffraction angle. Increasing the wavelength by keeping the slit width the same actually increases the uh, diffraction angle, but due to a lower de Broglie wavelength for the same spacing in crystal, this actually leads to or causes either, you could say, a smaller diffraction angle, that's one, or you could say an alternate answer would be smaller angle of intensity maxima, smaller angle of intensity maxima for each order, or decrease in fringe spacing. I prefer this one. Decrease in fringe spacing in diffraction pattern. This is the best one. So let me tell you the answer again. Due to the higher PD, electrons have greater momentum, which leads to a lower de Broglie wavelength. And this lower de Broglie wavelength with the same spacing in the graphite crystal causes a decrease in the fringe spacing in the diffraction pattern. That's essentially what happened over here, okay? And you didn't need to draw so many, as I've told you before, but it's fine if you draw more. Ultimately, more patterns would be produced, right? Due to the smaller, uh, you know, wavelength. Anyway, moving on to question number 8. Last 3 questions. We are going to be done soon, hopefully in 20 minutes. Table 8.1 shows some data relating to the properties of air, gel, and body tissue. The data are given to 3 significant figures. So show that the specific acoustic impedance of gel is this. So we know that specific acoustic impedance Z is defined as rho times C, speed times the density of the medium. So for gel, it's going to be this one. 1200 times 1400. 1200 times 1400 is 168,000, which is 1.68 times 10 to the power 6. 1, 2, 3, 4, 5, 6, right? So that is 1.68 into 10 to the power 6. So gel and tissue have the same specific acoustic impedance. Complete table 8.1 by calculating the missing values to 3SF. Use the space below for any working. Okay. So for tissue, 1.68 into 10 to the power 6 is equal to 1090 times C. So what is C? 1.68 into 10 to the power 6 by 1090. So C is actually 1541.28. So as you can see, all data is given to you know, 3 significant figures over here. So we should round this off to 1540. On the other hand, for air, Z 440 is equal to 340 times rho. So 440 divided by 340 is rho equals to 0.132. 440 divided by, I think I made a mistake. 440 divided by 340 is 1.29. Sorry, calculator error. 1.29 to 3SF. So that's it. 1.29. Fine. 1.29 and 1540. That's that. Use the information in A to calculate the So why was it given to 3SF? As you can see in the data, 3SF, 3SF, and yeah, this was also in 3SF, this was in 3SF, yeah. And they did tell us missing values to 3SF. I totally overlooked that, my bad. That was already mentioned. Now use the information to calculate the intensity reflection coefficient for the air tissue boundary. So why is a coupling medium like gel used? Because the difference in specific acoustic impedance of air and tissue is too high. So most of it will be reflected. But if we use the coupling medium, this reflection can be prevented, right? So what is the formula for intensity reflection coefficient? Intensity reflection coefficient is equal to is actually z1 minus z2 whole square divided by z1 plus z2 whole square. Fine. So let's input that. It's 1680000 1680000 minus air and tissue, right? So air is 440 divided by 1680000 plus 440, and this whole thing will be whole squared. So 1680000 minus 440 whole square divided by 1680000 plus 440 whole square. Now that gives us a value of 99%. Okay, 99%. One sec, let me check again. 1680000. Yeah, it's 99%, or to a fraction it is 0.99895, or since our data is given to 3SF, rounded off to 3SF, it is 0.999. Okay, so that is 0.999. And for the gel tissue boundary, we can just repeat the same thing. It's just that their values are actually the same, right? Their values are at the same at, it is 168,000 minus 168,000. I missed a zero over here. One sec. Divide by 168,000. 168,000 whole square. So yeah, anything 0 divided by anything is also 0. It's 0 by 0, which is 0. So basically, if we use the coupling medium, the intensity reflection coefficient becomes 0. So 100% of the radiation or the ultrasound is transmitted into the body. Use the answers in B to explain why gel is applied to the skin during ultrasound scanning. Okay, so the main point is, without gel, what happens? Without gel, almost all, 99%, almost all of the incident ultrasound is reflected from skin. Fine. But using the gel, with the coupling medium, with gel, almost all the incident ultrasound, almost all the incident ultrasound is transmitted into the body, okay? Fine, that looks good. We are good to go to the last two. Alright, let's move on. Question number 9. We are almost here at the end. Define half-life. So what is half-life? It is the time taken for activity. It is the time taken for activity of sample to half, and it's talking about the initial activity, right? Now, a sample contains N naught nuclei of carbon 11 and no other nuclei at time 0. Carbon 11 is radioactive and decays by beta plus emission to form boron 11. Carbon 11 has a half-life of 20 minutes. Boron 11 is stable. So boron 11 does not decay. Now, a sample contains N naught nuclei of 11, carbon 11. On figure 9.1, sketch the variation with time t of the number of nuclei of boron 11 in the sample. Okay, I'll teach you how. So at time t, I'm drawing this for carbon 11 at first. We start from N naught, and at 20 minutes, right? That is the half-life of carbon 11. At 20 minutes, it's going to become half of its initial value, and at 40 minutes, it's going to be half of that. So where is that exactly? 2, 3, 4, 5 over here. So at 40 minutes, it's going to be half of that, and at 60 minutes, half of that, and 80 minutes, even half of that. So 0.25 divided by 2 divided by 2, which is 0.0625. Half of 2.5 boxes is 1.25 boxes, 1.2 somewhere over here. So essentially, this is the graph, okay? This is the graph for carbon 11. So the graph for boron 11 should just be the inverse, okay? The graph of, this is so hard to draw on this graphics tablet. God damn it. Something like this. Now, same points, but boron 11 is going to start from 0. And then it's going to extend up here. It's going to go here. It's going to go up here. And then 1.25 from there. Here you go. Okay. So let's do it. I'm going to try to draw a smooth line. Okay. Damn it. There you go. Okay. So this is the variation for boron 11. Just the mirror image of carbon 12. Okay. Exponential extending from 0 to 80 with gradient of steadily decreasing magnitude. Line passing through 0, 0, 20.5, 40.75. Perfect. What's next? Explain with reference to the random nature of reactive decay why the activity of carbon 11 sample in B decreases with time. Okay. Good question. I haven't seen this before. So what does random nature of decay mean? We cannot predict which particular nucleus will decay. And every unstable nuclei has the same probability of decay. But if you decrease the number of unstable nuclei, the probability that one of them will decay also decreases, right? Because think of this. If you have 1000 die and you throw them, if you have 6000 die and you throw them, what's the probability of obtaining a 6? The expectation is 1 by 6 into 6000, which is 1000. Now if you reduce it to 600 die, yeah, the probability of obtaining a 6 will be the same, 1 by 6. But the number of 6s obtained will be lower, right? 600 times 1 by 6, which is 100. So if we decrease the total number of events or the total number of unstable nuclei, even though the probability remains the same, the number of successful events will decrease, okay? Because it's basically a probability. It's the activity is A is equal to n lambda. That's the main thing that you guys need to understand, that the activity is basically n lambda, okay? So this lambda remains the same. Now if you decrease the value of n, then the value of A will also increase, okay? That's the logic why the activity decreases, because A is equal to lambda n. Even though lambda remains constant, n changes, so A will also decrease. All right. So the concept is every undecayed nucleus has the same probability of decay. And what else? Since there are fewer undecayed nuclei remaining with time, since there are fewer undecayed nuclei remaining with time, so fewer will decay in a given time interval, right? I did not like their wording, honestly, but they did tell us to refer to the random nature of reductive decay. I would personally go for A is equal to lambda n, since lambda remains the same, probability of decay remains the same. If the number of unstable nuclei decreases, the activity must also decrease. I would honestly just give a mathematical answer, okay? But yeah, what else do you have to do? What else option do you have? Honestly, you have to memorize this. State with reasons whether a radiation detector placed near to the sample of carbon 11 indicates a measured count rate from the sample that is less than, the same as, or greater than the activity of the sample. Okay. So firstly, there is always background radiation present, and also maybe carbon 11 might be in a vessel like this. It actually emits in all directions, this way, 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 this way. But our detector is over here, the Geiger counter, okay? So we will only pick up this radiation, this one. So we will not pick up these, so we might get less. Also, what else? There might be a dead time of the counter, which is a problem with the instrument, and there are other points, okay? And some might be absorbed within the air before reaching the counter. Those are other common points, right? So let's write down the answers. State why, with reasons, whether radiation detector placed near to the sample indicates a measured count rate from the sample that is less, same, or greater. Let's start. So mostly it will be less because we are not picking up most of the radiation, right? That's the main issue. So let's go for it. The sample emits in all directions, but the detector only captures emissions in one direction, as I've told you, the orange arrow. Next, what else do we have? Some emissions are absorbed before reaching detector. Fine, by the air, maybe. So it doesn't even go to the detector in the first place. And some emissions are scattered within the sample. This is also true. Some emissions are scattered within the sample. Fine. So we have 3 marks over there. And what else? Simultaneous arrival of multiple particles only registers once. That is called the dead time of the counter. Basically, the counter has a time period before it can reset again. So if a lot of radiative particles reach the counter simultaneously, it will only register it once rather than twice, okay? That's the dead time of counter. Simultaneous arrival of multiple particles. Maybe 3 or more particles came to the detector at once, but the detector would only register it as one count. As a result, we would be getting a value that is less than the true value, right? It will be underestimated. Simultaneous arrival of multiple particles only registers once. Fine. And what else? Some particles may reach a detector but not cause ionization. Interesting. I haven't seen this point before. May reach the detector but not cause ionization. Okay, so if you write these 6 points, any two of these, you could write any two of these and you would get 2 out of 3 marks. So what do you need to write to get the final mark? This is the most important point. We gave explanations. So now finally the measured count rate is actually less than the activity. Okay, so the measured count rate is actually less than the activity due to all of these reasons. Fine. Finally, we have reached the end of our paper, question 10. A huge paper, very taxing. I'm only doing this for your exam tomorrow. State Hubble's law, identify any symbols that you use. Very, very important. Hubble's law states that speed is directly proportional to distance. Okay, speed is directly proportional to distance. And what else? We use a constant actually. This is the formula of that. V is equal to h naught d, the Hubble constant. Now we need to explain what these are. So basically, the speed v is the speed of recession, right? Speed is actually, this is how they wrote it, speed of recession of a galaxy from an observer of a galaxy. From an observer. And what is d? And distance d is the distance of the galaxy from the observer. Okay, of the galaxy from the observer. This is the gist. Speed is the speed of recession v from an observer, and distance is the distance of the galaxy away from the observer. Now, speed of recession means how fast it is moving away from the observer, right? Now we have a star of luminosity, and h naught is the Hubble constant. A star of luminosity 3.8 into 10 power 31 watt is a distance of 1.8 into 10 power 4 meters away from the Earth. Now, calculate the radiant flux intensity at the Earth of the radiation emitted by the star. So we know that the formula for radiant flux intensity is F is equal to luminosity divided by 4 pi d square, where d is the distance. So this can be the star and the Earth is over here. So we know that the luminosity is actually spread out in a three-dimensional space, which is like a sphere. So this is the distance or the radius of the sphere, and since it's three-dimensional, we have to take the total surface area of the sphere, which is 4 pi r square, and here the radius of the sphere happens to be the distance between them, right? So what do we get? The radiant flux intensity equals to luminosity 3.8 into 10 power 31 divided by 4 pi times 1.8 into 10 to the power 24 whole square. Let's do that. 3.8 into 10 to the power 31 divided by 4 pi into 1.8 into 10 to the power 24 whole square. Okay, so F is actually 9.3 into 10 power minus 19. I'm opting for 2SF answer because my data is given to 2SF. Now the star in B is a distant galaxy, is in a distant galaxy. A spectral line in the light from the galaxy is known to have wavelength 486 nanometer. This spectral line in the light from the galaxy observed on the Earth has a wavelength of 492. So as you can see, the observed wavelength is greater than the actual wavelength, the laboratory value. Why is this? An increase in wavelength is basically the Doppler redshift. This is proof that the universe is expanding and the Big Bang took place, and since then the universe has kept on expanding and has never stopped. Because you know that when an object moves away from you, the frequency decreases and the wavelength increases. Explain why the wavelength observed on the Earth is different from the wavelength that the galaxy is known to have emitted. The logic is the galaxy is moving away from the Earth. We are the observers on Earth, is moving away from the Earth, and wavelength is increased by the Doppler effect or due to redshift, right? The wavelength of this light from galaxy wavelength of light from the galaxy increased by the Doppler effect. By the Doppler effect, yeah. Or you could just say due to the redshift, Interesting. Now, final answer. Finally, determine a value for the Hubble constant, h naught. Now, we have to use the formula that I mentioned up top. But before that, I need to find out the speed of recession. How? Using the formula for Doppler redshift, which is given in the question paper. It's over here. This one, Doppler redshift. So we know that del lambda by lambda is equal to v by c, where v is the speed of recession and c is the speed of light. So what is the change in wavelength? It is basically 492 minus 486, which is simply just 6. So 492 minus 486 by, always remember, the original one, 486. The truth, not the observed one, is equal to v by speed of light 3.00 into 10 to the power 8. So if you do solve this, what do you get? 492 minus 486 by 486 into 3 into 10 to the power 8. So we actually end up with v is equal to 3.7 into 10 power 1, 2, 3, 4, 5, 6 into 10 power 6 meter per second. Now I just told you that, v is equal to h naught d. You know that v is equal to h naught d. So ultimately, h naught equals to v by d, which is h naught equals to 3.7 into 10 power 6 divided by the distance between them, right? 1.8 into 10 power 24. 1.8 into 10 to the power 24. That gives us a value of h naught is equal to 2.1 into 10 to the power minus 18. 2.1 into 10 to the power minus 18 per second. Okay, that is it for us here. We are done with the paper. Overall, very difficult paper, honestly speaking. That is why so many of you have requested me to solve it. Personally, I haven't struggled anywhere in any math. I just felt like the table was quite complex for a lot of you guys. I might have made a mistake here by drawing a straight line instead of a curved line. Other than that, everything seems all right. Everything seems all right. But overall, difficult paper, and some marks might have been lost. Where this theory, I might have lost 1 mark in this theory, and then in the theory for the diffraction grading one, right? Maybe 1 or 2 marks might have been lost. But yeah, there's nothing to do in a huge paper like this where there's theory involved. You might lose 1 or 2 marks here and there, okay? And remember that the definition for gravitational field strength and electric field strength has changed. It has turned into the definition for electric field strength and gravitational field strength instead. And yeah, all these topics are high yield for your exam on the 9th of October. So please look into this along with the other papers from 2023 and 2022 and 2021. I'll link those at the end, and you can also find it in a in the playlist. Also, before finishing the video, I just wanna provide some clarification on the other variant that I've done recently. In the comments, some of you did point out that a particular question could be done in a simpler way. So let me just look into that. Okay, so here we are. So I wanted to provide clarification on the ideal gas question. Here you go, this one over here. Yeah, this cycle. An easier way to complete the table actually, right? So for the change from A to B, clearly I told you that since volume is decreasing at constant pressure, work is done on the gas, so work done must be positive. Okay, and now we can simply use PV is equal to nRT to find out the change in internal energy. How? Check this. we can use the formula PV is equal to nRT, and we can make temperature the subject. T is equal to PV by nR. How is this relevant? Because the volume has decreased from A to B, nR have remained constant, P has also remained constant, but V has decreased. Since V decreases, T will also decrease, right? And since this is an ideal gas, clearly stated before, you guys know that I've mentioned in this particular video that typically internal energy is Ke plus Pe, but since it has no IMF, the internal energy is simply equal to Ke, and Ke is equal to 3 by 2 Kt, right? That's the concept. So we can say that U is also proportional to the temperature only. So if volume decreases, given that Pn and R are constant, T will also decrease. So if T decreases, the internal energy must decrease. That is why we can give a tick mark over here, rather than the longer explanation I gave here. Although that was required for writing the answer for part 2, but you could solve the table easily like this, okay? And what else? What about this tick mark over here? Same concept applies, check this. As you go from B to C, yeah? As you go from B to C, this change occurs at constant volume. So let's go again for B to C. You know that PV equals to nRT. So T is equal to PV by nR. Similarly, nR remains constant, and over here the pressure does actually increase. Okay, the pressure increases, so it might indicate that um, given that volume is constant, it might indicate that T also increases, right? T also increases because in the last one, when volume decreased from A to B, given that everything else was constant, T must also decrease. And here we can apply the same concept. Since nR remain constant as well as V, as we are moving vertically upwards, only pressure increases. So if pressure increases, then T must also increase, and that is why internal energy must also increase. Since for an ideal gas, the internal energy is solely dependent on kinetic energy, and kinetic energy is equal to 3 by 2 kT. So that is the logic behind this. That's how we can fill up the table really easily. And for this question over here, we had to talk about U is equal to Q plus W. Okay, that explanation was overall fine. That more work is done by the gas in CD, okay, then compared to AB, or else it wouldn't match. That is mentioned in my video over there. But yeah, I'll just link this part in the comment section and description box for my solve video for paper 4-1. And thank you for pointing this out, pointing this easy way out in the comments. And if I did make any mistakes or solved any questions in a rather lengthy way, please do comment below. And yeah, that's been it. So if you've liked the video, please do subscribe to the channel, smash the like button. It helps with the algorithm a lot. Consider supporting me on Patreon. And yeah, quick reminder to you guys, quick shout out to my top tier patrons for the month. For this month, we have Dewa, Luna, and Sean supporting me. They're my top tier patrons. So if you want to be featured on the end screen, please do consider supporting me on Patreon. And we've recently launched our Discord channel, so you can also join us there. And you can, drop by and post your problems. I'll solve them when I'm free. And yeah, please do download question papers from our site. And I'll link the paper for May-June 2023 variant 42 up here, and the paper for February-March 2023 variant 42 down here, and the playlist for physics P4 up here. And remember to subscribe to the channel. See you guys. Bye bye.